Okay. All right. Thank you. All right, thanks for people sticking around. I know it's getting a little late. And first off, let me just congratulate both Joe and Steve. It's been a pleasure to be essentially the middle of the sandwich here, where I'm inspired by both working with these guys in many different contexts. For Joe, it was really, I came from a very small place, and I went to Northwestern, and I saw there's all these great people that were collaborating and had all this expensive toys. And for me, it was just like a kid in a candy shop. I could walk up to people and ask them how that works, and they would explain it to me. And this really helped inspire my early days as a scientist, moving on to my own program. I'm going to talk in honor of Joe a little bit about what I consider, most people have their favorite materials, and I think for Joe, one of them is TiO2. He spent so much time trying to understand it. For Stephen, I'm not going to really highlight anything, but what you saw in the last aspect of this, and really, I think when he came to me, he wanted to do something new, and part of this was how can we make materials that are pure, but also really understand their electrochemical properties. And at the time, a lot of people were growing all sorts of different nanotubes, nanowires, and this sort of thing, and they really had poor characterization. And what we found out of that is that we came up with a method to make really pure materials, and then we could understand their electrochemical mechanism for all sorts of contexts. My student, Jake Gorham, is going to talk about these electrodes with regards to biosensing and looking at enzyme immobilization. Okay, so of course the motivation to a lot of this work that I want to talk about is really we want to be able to come up with energy conversion or electrochemical energy technologies, and we've highlighted for the focus of most of our talks things that we typically want to convert a chemical fuel into electrons or vice versa. We want to use electrons either garnished from the sun or from some half reaction to then store a chemical fuel which we can then use as a commodity or recycle, go to a carbon neutral type cycle. I'm not going to talk about any of this. And then there's also technologies that can go to really fast rates, which we typically talk in the context of power, where we can actually store charge very quickly at interfaces. And then in the intermediate time scales, these are battery type technologies, and if we can reverse the charge half reactions back and forth, we can make a rechargeable system. Okay, without going into a lot of detail, I say one of the biggest problems is that these all involve very complicated interfaces, solid-liquid interfaces. Typically, the electrodes that are solids are composite materials that are made up of all sorts of stuff, not only just the active material, but also binders, such as activated carbon, and then some type of polymeric glue that holds it all together. And that's found in all three of these types of applications. So one aspect is where we can start. And so I'm just going to talk primarily about rechargeable lithium-ion batteries. We've had a large DOE-funded center that focuses at looking at the fundamentals of how charge, in particular lithium-coupled electron transfer, occurs at these interfaces. My colleague, John Goodenough, is a part of this effort. I don't know if you know this man, but he is a physicist by training, and he actually is the guy that's responsible for all of the commercialized cathodes that have been invented that go now into our portable electronics and in a lot of these advanced lithium-ion battery materials. And he recognized very early on that you could tune the redox potential of a solid, and by substitutional adding ligands in a sense, right? We can think in the solid state sense, not the molecular sense, where you actually can raise the oxidation potential of the cobalt 3,4+ by putting in phosphorus rather than oxygen. Okay, and so these potentials get so high, oftentimes that falls outside of the potential window of stability of the solvent that holds the lithium ion salt. And so, in fact, a lot of these materials can be made by high temperature solid state synthesis, but we can't study them because we have huge degradation problems, decomposition layers that form due to these highly oxidizing potentials. The same is true for other anode materials that you might have heard about, the silicon and the tin analogs. And the reason why those are interesting is because they have much higher energy storage densities, the amount of lithium you can store per redox state relative to graphite. Graphite's unique in the fact that it actually forms a passivating layer spontaneously that protects this low potential. and that prohibits things like dendrite growth in the short circuit of the battery. All of these issues, though, in general, if you want to be able to adopt this kind of scheme to go to more powerful, i.e. widen the voltage window, P equals IV, or higher energy densities by fundamentally changing how you store lithium in these types of materials, you have to worry about, again, a whole bunch of complex chemistry that occurs at interfaces. So, of course, we can choose different materials to study, but this is just a kind of a summary of ones that we've looked at. Also at UT, we have really good solid-state people like Mantherum and Goodenough, and they're making things that are very complicated chemically. Most people look at this kind of nomenclature and they're just freaked out from the standpoint of how complicated, how many different transition metals, how the crystal structure influences that on top of the morphology of these things. So what makes these very difficult materials is that they're both chemically complex, trying to understand the redox chemistry of these different transition metals in these oxide matrices, and how lithium coordinates to those different sites, but also how the issue of morphology and size lead to certain predictive behaviors, such as scalability, of when something goes small or gets big, what limits the lithium ion transport in these materials, and also what influences the degradation chemistry that can occur as a side effect. So, of course, one of the challenges that I focused on a lot in my career, in fact, when I went to Northwestern, Joe had an ONR proposal that said that we could actually try to develop technologies to look at pH jumps. So it got to this issue of Tom pointed out, summarized by Susan Yan's work and Buford Lemon and Lyon before that, where they saw that the conduction band of TiO2 could shift as a function of the pH of the solution, and trying to understand when you actually cycled this in the presence of lithium perchlorate, how did this band move? And Tom explained this, in fact, found out the real reason as to what those electrons are and where they accumulate. Okay, for me, I was more interested in trying to control both the material, so I knew I had phase pure stuff, but also develop a suite of techniques where we could image the spatial heterogeneity of the system, and then try to understand, as a function of the electrochemical conditions, what is contributing to the material's behavior in the context of ion storage. So I moved away quickly in Joe's group from the aqueous solutions, because the problem was you have things like hydrogen evolution, oxygen evolution, bubble formation, dealing with very concentrated acids, and we moved into actually trying to do this first with lithium ions. So the modern advantages to several of the techniques that we've been developing is to really look at the spatially resolving power of light microscopy coupled with vibrational and spectroscopic techniques, where we can then use a series of these tools to shrink down the analytical spot size so that we can focus on issues of understanding how heterogeneity matters in this, and get away from kind of these ensemble average measurements where you get convolution of the analytical signal. Okay, so in our center, we actually focus on many different problems with many different materials. We can synthesize materials libraries where we can change both the morphology and the size and look at the ladder of complexity that goes across that phase space. We can do high-resolution analytical electron microscopy. And also, and now what's big is mesoscale type assembly of porous materials where there's a lot of interwoven porosity in these sorts of things. So synthetically, we can think about using different approaches to control the complexity of these new materials. But we also want to couple that to understand the mechanism of how these different aspects govern the charge-coupled electron transfer dynamics. And so we've invented things like in situ Raman, where we can actually put this in a coin cell environment and cycle it like a regular cathode or anode material. And then we typically can couple that to high-resolution theory with Graham Hinckelman at UT Austin and understand about what would be the actual electronic structure, what would be the actual structural dynamics that could occur as lithium diffuses in and across these types of complex architectures. And so we want to be able to merge experiment with theory to really gain fundamental understanding of this. So one system, because it's TiO2 based, and I want to just calibrate people, is everyone's probably familiar with anatase, right? This Degussa TiO2 that's sold commercially as a powder. That's essentially a thermodynamically stable phase. The most thermodynamically stable phase, if you heat up anatase, will turn to rutile. But in the new synthesis techniques, people have discovered this intermediate kinetically metastable phase that's known as TiO2b, or bronze for short. It's got a different crystal structure, but this is primarily done by low temperature synthesis. It's ion exchange, typically from sodium and potassium titanate structures that dehydrate to form crystalline TiO2b, and this can be tuned in terms of its size and the architecture. You can make nanowires, nanorods, nanoparticles, mesoporous networks, and so forth. So we can then think about not only the size and the shape, but also the architecture, making interpenetrating mesoporous networks. Titania, from a lithium-ion battery standpoint, has always been of interest for a long time, but in the bulk form, it doesn't do very well in terms of the reaction with lithium. But by going to nanostructuring, it was predicted that you could access a more higher kinetically lithiated stable phase. And so we wanted to actually show what the kind of design rules were by being able to go in controlling these material size and morphologies for this new polymorph. Okay, so we summarized all of this in this nice accounts article by my postdoc, Tony Dilla. But what you find is if you actually look at the amount of lithium that you can store in TiO2b of these different polymorphs, the TiO2b is very interesting because in the bulk, you still start to access very high lithiums where you get roughly 0.85 lithiums per titanium site. If you go to smaller nanoparticles, you actually can lithiate 1 titanium site per lithium. Other structures, it's well known in the bulk, they don't lithiate very well, but if you go to smaller sizes, it's now been shown by Wagmacher and Bruce Dunn and others that you can actually start to access more stable, kinetically stable, higher degrees of lithiation in these materials. Okay, but of course, then you can ask the question: is where does the lithium sit in these crystal structures, and what is the oxidation state that governs the lithium-ion electron transfer kinetics of these sorts of processes? So in one system, we were actually able to come up with a very precise synthesis where we could make titanium nanosheets that were two-dimensionally analogs of something like graphene, okay? And this was done by actually using ethylene glycol and isopropoxide, and the ethylene glycol binds to one particular crystalline face, and it limits the growth into two-dimensional sheets. We could also then use the same precursors in the absence of ethylene glycol and make nanoparticles of the same phase. So we had control over both the morphology, the dimensional confinement in this case, but also the particle size. And what we found in this work is what we're doing here is we're doing galvanostatic cycling. That's basically monitoring the change in voltage as we titrate at fixed current, a certain amount of charge. And if you take the derivative of that with regards to the IV curve, what you get is a differential capacity plot. This is the integrated charge with respect to the change in potential. And so what's plotted here is the lithiation going in this direction, going down, and the delithiation. And what's not at this particular time when we did this work, it wasn't understood why you get different staging of the lithium insertion into this particular material. And we were able to couple this with high quality DFT calculations performed by Graham Henkelman. And so what we were able to find in this is that if you use nanoparticles, you'll get appearance of two different peaks, basically these two different energetic potentials where lithium sit at certain sites within this TiO2 crystal. There's actually 3 sites that could be lithiated, and in this particular case, it's this A2 site that starts to lithiate first, and then the A1, and then there's a filling of the A and C sites down here. For the nanosheet, because we confined it into 2 dimensions, basically that energy potential dependence spreads out, and the ordering at which sites fill first switches, so we actually can fill the C sites first, then A2, and then A1. And this explains both the shape of these typical cyclic voltammograms, if you want to call them that, and the reversibility. And the hysteresis in the lithium insertion and deinsertion is related to coulombic interactions within the number of sites that can be lithiated. And so the theory actually bears this out. Okay, the other thing that we were able to show, we were able to follow, is that when you actually make this material, you can heat it up and you can convert it into the anatase phase. And through using Raman spectroscopy, we could actually build a materials library and use the vibrational fingerprint to identify whether we had nanosheets, nanoparticles, or anatase. We could then heat up the TiO2B nanosheets and watch them convert into nanoparticle morphologies as evidenced by the change in these different frequency of the vibrational modes of the TiO2 and these phonon modes down here. And then we could actually see when anatase starts to nucleate into this particular TiO2B phase, because anatase has a much more simplified vibrational spectrum. The other thing that we could do is we could take the nanosheets in a flow cell in the presence of oxygen and heat them up and watch the Raman spectroscopy convert. And so what's shown here is basically at room temperature, we got something that looks, again, like the nanosheet morphology. As you start to heat this up, you start to see the formation of the nanoparticle structure, something evidence of the sheet converting into a nanoparticle of TiO2B. You then get decomposition of the ethylene glycol and molecular fluorescence that's formed due to the capping ligand on this nanosheet that controls this particular morphology. And then as you get hotter to about 300 degrees, you can see this main peak that's missing down here that's the anatase signature. Okay, so interpreting this, of course, this is a small analytical spot size, about 2 microns, but it's still not good enough to really recognize whether you have intermixed phases and what would be the phase transitions between these particular materials thermally. But we found that we could make electrodes without any binder and look at the scan rate dependence for the nanosheet morphology converting into a nanoparticle and then the formation of anatase. And so here shows the cyclic voltammetry of these thin film electrodes, room temperature, heated up, watch the growth of another peak growing in as evidenced by the formation of the nanoparticle morphology, and then start to see another peak out here, a much higher potential that's associated with anatase. And we can actually follow the scan rate dependence and say something about the kinetics for lithium insertion and the charge storage mechanism. And the other part of this is that if you look at the high resolution electron microscopy, it's not just a simple case of the nanosheet folding up into a nanoparticle. What happens, if you look really closely, is you start to see nucleation of little nanoparticles within the sheet morphology, which is a little bit contrary to what you might at first think about in your brain. And then you start to form large domains of TiO2B within that nanosheet and separately anatase particles. So it also it's not a continuous phase transition where you form a nanoparticle of TiO2B and then it converts into anatase. It's much more complicated than that, which we haven't quite fully understood. But to summarize this particular thing is that the reason why you can get such high lithiation has to do with the fact that this is all surface. And so this is what we consider a redox pseudocapacitive mechanism where all of the lithium ions are stored right at the surface. In anatase, when you form that phase, it actually looks much more diffusional based on the scan rate dependence. And these other 2 peaks that grow in for the nanoparticle geometry have to do with the change in the filling of the number of sites and the energetic dependence on that. In particular, when you make a nanosheet, you get compression along one axis, and that makes the C site more stable for lithiation, and that actually lithiates first relative to the other sites in this particular structure. Okay, we went back to the literature to try to understand this, and we found, of course, these papers, we actually knew about these papers before we even made TiO2B, where early on Gretzel reported that you'd get these surface waves in anatase, what she was trying to template into this mesoporous network, and he thought that these were just amorphous TiO2 phases with anatase crystals embedded in them. And so people started to investigate this as they started to make different nanowires and nanorods. But really the short end of the story is the sad merging of a theory where they did calculations and compared it to phase impure materials to try to understand which sites fill first. And so this labeling of the C site in TiO2B nanowires is really not the case because this is the anatase peak. And it's these other 2 peaks that are related to the geometry of this nanowire that are still very surface-oriented in terms of how they lithiate. Of course, we don't really have a good spectroscopic handle, and we wanted to get more sensitive in terms of what type of chemistry is going on when we lithiate and delithiate these materials. So we've gone to this kind of spectroelectrochemical platform where we use optically transparent carbon for a number of reasons. One is that you can make it really flat and it's still conductive. It's also transmissive in the UV, so this allows us to actually measure the change in the spectral characteristics across a very large window. Of course, we then wanted to make a very well-confined model electrode on this, and Joe talked about using ALD. It's really amazing how well-controlled this process is, where you do grow things in a layer-by-layer assembly. And so there's a lot of advantages of this in the fact that it's not line of sight, so you don't get some type of shadow effects, that the precursors are pretty much reactive at room temperature or slightly above temperature, so you don't have other heat-driven factors that change the nucleation and growth behavior, and that it's truly one layer at a time, so you get really good control over this. In our case, we use precursors tetrakis dimethyl amido, and we pulse that in on a hydroxylated surface. We use plasma, a little bit of a plasma treatment to nucleate that first layer, and then you pulse in the water to then nucleate the next phase. So when you actually get into this business, what typically happens is people buy commercial instruments and they sell you recipes, right? And they say, well, if you want to grow TiO2, this is the precursor and this is the pulse sequence and this is how many layers. And what we found, though, is that actually you have to be careful about understanding where the nucleation occurs in the growth. Joe showed an elegant example about how they can really control this at the molecular level and functionalize individual sites that are separated by quite some distances. In our case, our focus is really to grow a stable TiO2 layer that's very thin so that we can study the thickness dependence of the lithiation of this material. And if you get this right, you can actually make phase pure anatase. You can't make phase pure TiO2b. I wish we could get that to work. But all of the particular things that we do in order to try to understand the structures, we could do Raman. In particular, if you look at XRD, you get nanocrystalline anatase. Roughly the average crystallite dimension is about 13.5 nanometer. Therefore, the optical gap of this is actually larger than what you would expect for large crystalline TiO2 anatase. So there's a confinement effect. And if you predict, based on the number of sites, you would predict that roughly you could lithiate for TiO2b about roughly 335 milliamp hours per gram. Multiply that by 3, and that's coulombs per gram. Whereas the other materials have been shown to not lithiate as much. Okay, if you cycle these electrodes in the conventional battery electrolyte, lithium hexafluorophosphate with dimethyl and diethyl carbonate, ethylene carbonate type structures, here just shows an example of some of these electrodes. Here's an 18 nanometer thick TiO2 anode. This is flipped on the scale. I apologize for that. One student plots it by the UT conventions, the others plot it by the battery conventions. But this is the reduction process. And you can see at very high potentials, you see this peak that starts to diminish after consequent cycling, and then you see this kind of stabilization occur. We also can do this as a function of the electrode thickness and superimpose where these particular things occur. And this is actually after the 5th cycle superimposed on each other. And what you actually start to see is more hysteresis in the delithiation as you get thicker films, and also this other chemistry that's occurring at much higher potentials than where the anatase was known to lithiate. So this immediately then began to confuse us in terms of what type of processes are occurring at the surface. What type of surface chemistry is controlling this type of behavior and this degradation process? In a sense, the battery people would call this irreversible capacity loss, because this process is associated with loss of lithium from the electrolyte. And so since you can't reoxidize that particular process, you basically lose lithium with every charge and discharge cycle. It's very, very important to understand that type of trapping process. Okay, so of course we could do spectroelectrochemistry, and we could actually monitor as we lithiate where the electrons are going. So this just shows the absorbance as a function of wavelength. And you can see that out here in this near-infrared part here is where most of the absorption increases when you lithiate. So Tom talked about this. This is basically this Drude edge-like behavior where you have these free electrons in the conduction band. And in the gap of this, the gap is actually attenuated. So it looks like it gets a little bit bigger, and so the absorption goes down. You can't do this on ITO because ITO interferes with this. Of course, you can plot the derivative of that absorbance with respect to voltage and superimpose that on the current, and you can actually see that this main peak here is where the lithiation is occurring, where the electron's being transferred. And there's all this other surface chemistry that doesn't show up in the spectroscopic signature, that is reporting on the charge. Something is being transferred across that interface that shows up as coulombic charge. And of course, in order to answer this question, we need to do very sensitive surface analysis. So we've also, in various other contexts, developed a transfer capsule that we can transfer out of a glove box and not expose this to water or air or any other type of reactive environments under positive pressure, and then we can gently pump on this and remove any solvent or any of the inert gas in this particular case before we load it into the XPS chamber. And so this also requires a little bit of gentle treatment. We can wash this electrode from a flood cell taken from a glove box with DEC, which is known not to solubilize those surface products. And then we do a soft little gentle bake to get rid of any excess solvent. And then we can stick it into an XPS or TOF SIMS for the surface analysis. Okay, those of you that have done any spectroelectrochemistry of TiO2 would say, well, is it electrochromic? Does it turn blue? Right? And this has been known for quite a while. If you have a single crystal of anatase, it's not very good, right? But if you make nanocrystalline anatase, you can actually make a pretty good electrochromic device out of it, i.e. that there's a lot of surface to volume ratio, there's shorter transport lengths, but people really haven't understood what does the blue color do to. And Tom explained, in a sense, what that is now. But if you look at the actual XPS of lithiated anatase, these thin films, versus the delithiated ones, we actually see no change in the oxidation state of titanium. And so it's not just that we reduce titanium 4 to titanium 3 and it turns blue, that there's other trapping mechanisms that don't report on the change in the oxidation state. And so in this particular case, XPS really isn't that sensitive to really see if we actually have a small amount of titanium in there. But we do get lithium in these lithiated films, but no growing in of that titanium 3 signal. However, what we can do is we can put it in the TOF SIMS and we can do depth profiling of the compositional change of lithiated TiO2 films versus delithiated films that have been cycled. And so I know this is a little bit complicated and hard to see, but this marker here for fluoride minus, for the electrochemically delithiated films, you can see that it's pretty much confined right at the interface by this dashed line. This is the surface chemistry. This is where the TiO2 film starts. This other line marks the interface between the carbon and the TiO2. And then we've fabricated this on quartz. And so this is the other interface here. So we get very precise alignment with these different interfaces. Because it's so flat, we get very good depth profiling for these particular materials. And we can actually look at the following of where the oxygen is in the titanium film that's co-localized with TiO2. The signal is not quite as big, so they're normalized mainly to this peak here. And then where the lithium is, it's primarily trapped at the interface. If you compare the films that were cycled and then removed under lithiated conditions, what you see is actually there's this large predominant peak, lost my laser pointer, right here reporting on the fluoride content, and it's actually all the way through the TiO2 film and actually goes into a little bit of the carbon. And of course here's the lithium that's also going in, and it's co-localized with the titanium. The other thing that's not reported here is that we actually, when we sputter and we do mass analysis, we can actually get, since it's time of flight, products that look like they're fluorinated titanium oxygen species. So these are titanium oxyfluoride type species. So to me, this was actually really surprising. I could not understand why you get so much fluoride that goes all the way through the film. And it looks like it's reversible. So when you actually delithiate, most of the fluoride comes back out. So we thought about this in another context. And It has to do with the fact that the salt itself can decompose. And so some of this surface chemistry is really controlled by when you make materials, especially titania. If you have surface hydroxyls, those can be reactive, especially in the presence of lithium salts. What's even worse is if you have the hexafluorophosphate anion, it's not as thermally stable, and in particular, that can actually decompose to form PF5, which then reacts with water to form HF. This is a gaseous species, so then it evolves out of the cell. But then once you've made HF, that HF can do a lot of different things. It can react with the lithium to make lithium fluoride, which is basically an insulator, and block electron transfer across the interface. It can get trapped into these other types of products, lithium carbonates, for instance. But what we noticed was that if you actually generated HF, that you could actually start to make surface hydroxyls due to this exchange process. If this was a lithiated state, there's other degradation mechanisms that I won't get to, but in the delithiated state, if you've created any surface hydroxyls, you can get direct reaction of the HF to make more water. That is a catalytic cycle, because if you put water in, PF6 decomposes to make more HF, so you've got a lot of recycling in this. In addition, if you actually look at, most people think about lithium insertion in titanium, or proton insertion, is they typically talk about cation insertion. But in the presence of HF, you can actually reversibly not only lithiate this material due to the electron transfer from titanium 4 to titanium 3, but you can do anion intercalation due to exchange of the surface hydroxyl fluorine couple. And so this has actually been proposed mechanistically by us in a different context for vanadium oxide. It's even worse, actually. It turns out that this happens at open circuit, where you get bulk formation of these vanadium oxyfluorides. And recently somebody also showed a very similar mechanism for the formation of silicon oxide layers on silicon that then makes silicon fluoride at the surface. And so we think this actually helps understand why you get extra charge storage capacity, but also you get all of this degradation chemistry that occurs at much higher potentials. So you're doing a conversion reaction that's reacting with both the lithium and the fluoride in this particular case. It's a mechanism that people really haven't firmly established, but I think it's very important, especially if you're using reactive anions that can decompose and make reactive species like HF. Also, what I've tried to cover in a broad sense is that this idea of making your own materials, especially metastable phases, low temperature phases, things that are driven to the thermodynamically stable phase, allows you to tune both the nanostructure, morphology, the pore size, a lot of these properties that people now call mesoscale science, something that Joe was a pioneer in, using molecular building blocks. And then really you still need to develop these more state-of-the-art electrochemical studies so that you can really follow structure-property relationships in a more intimate way to understand the mechanism. And what's come out of this work is really that you can really do much higher level of capacitive energy storage with these nanostructures. And if you can stabilize the surface chemistry, these might actually be the types of things that could go into some of these advanced energy storage technologies. But by nature, because they're nano, they're also more reactive. And the surface chemistry makes them much more of a more difficult analytical problem to understand. So with that, I just want to thank, most of this work was really done by one person, Dr. Anthony Dilla. He's looking for a job right now. I think, he's a really good guy. He's a little bit understated, but he's really helped us understand across all these different polymorphs what the type of mechanisms are. The ALD work was done by a newer student, Matthew Charlton, who really figured out how these ALD films grow on carbon. They actually grow faster on carbon than they do on silicon, which is something that we at first didn't quite understand, but now we do a little bit better. And then, of course, most of this work is funded by the Department of Energy. Thank you. Yeah, well, okay, one is you got to be careful about XPS, but the penetration depth of these films are all the way through pretty much. And because we don't see any titanium-3, it tells us something about most of the initial of these films, the ALD films, because they're driven by the formation of these hydroxyls to grow the next layer, that there's a lot of hydroxyl chemistry. So that first peak that attenuates after each cycle really is conversion of the surface hydroxyls, most likely, to react with either lithium or conversion in the presence of the PF6 that decomposes to make HF. And that is not really been described. People think titania is really dimensionally stable, but again, with these ALD films, they're really flat, and they're really model interfaces, so we get good clean spectra with these. And then the other stuff is that if you notice that in the thicker films, there's a hysteresis in the lithiation and delithiation. But if you actually have a partial conversion of the oxygens with the fluorination process, that could lead to other kinetic barriers to moving lithium through the film. And so that might be related to that you have both mechanisms occurring, and they're both reversible in some sense.
Keith, I'm going to have to read your Counts article and the papers that flow out from this, but it's really striking that titanium doesn't have any electrochemistry. But, I mean, by your XPS measurements, does that mean you could look at something like zirconium oxide? You don't need redox activity on the metal center anymore?
No, I think it's both. You have to have both. There's still redox activity for both. I think it's a little bit hard to interpret the XPS results. We need to do a lot more work to, repeat them. But, you can have a concerted reaction, in a sense, where you have both electron on the transition metal, that's the classical intercalation, but then you also form surface hydroxyl type species that are peroxo-hydroxyl intermediates. And so, as you know, in these perovskites, which I didn't talk about, we think that it's driven primarily by vacancies and the lattice hydroxyls that go from water oxidation to then hydroxide that is reversible.
You've got to be able to cycle through titanium-3, but it's, at the end of the day, there's no...
Yeah, who might be that there's another reaction that then reoxidizes it. It could be that they didn't transfer the sample right, but...
And does it get all simple and not very interesting if you replace BF6 with some other anion?
Well, lithium perchlorate, which you see, you don't see any. Well, there's a little bit of trace fluoride in there, so it's a little bit not as clean as you'd like. But we actually have done things by putting tertiary amines. They're HF scavengers, and yeah, in this vanadium oxide paper, we showed that they're pretty stable. But but if you make really high surface area materials in the presence of HF, good luck. If you have any oxides, you can get bulk conversion at open circuit. And what we're finding with the vanadium-based phosphates in these battery electrolytes, the vanadium is really mobile. It comes out, and then there's a lot of degradation chemistry that occurs on the oxidative side instead of the reductive side, which I showed for TiO2. Yeah. Okay. For oxides, I would say that you got to get rid of the hydroxyls. Lithium in the presence of hydroxyls is bad news. All the battery people always talk about water processability. Forget it. I think that's largely when they cycle these materials, all that irreversible capacity loss in the first couple cycles all has to do with just surface chemistry because you've got water around and it acts as a getter, especially if you have oxides with surface hydroxyls. And even the hematite system, right? That's even worse if you try to use that as an anode because of those surface trap states like what Tom talked about.
I'd like to thank all the speakers for this terrific session.
Okay, so if I could ask members of the Society for Electroanalytical Chemistry to just give me your attention for about 3 minutes for our annual business meeting. By the way, for the tech, we don't need this portion videotaped, so